Um, Hello everyone, and welcome to today's talk about It's Never DNS. And before we start the actual presentation, my name is Karen, and I'm representing DevOps Malmö. I'm organizer of DevOps Malmö. It's been 5 years. We are organizing events, and the main thing what we are trying to do is share knowledge between us. So if you are a cool company or cool person and want to present something nice and share with the community, feel free. It's non-profit organization, so we do not earn any money or we don't share any money, okay? The only thing sometimes we get is like some big conferences, they want us to get some promotion, and we get some free tickets to share. So you have been looking at them in, like, if you are following my LinkedIn, try to like give some free tickets to some conferences, okay? That's the only thing we get as a benefit. The rest is all about you, so you bring the knowledge, you share them, all right? If you want to know more about us, you just Google DevOps Malmö. We have like account in meetup.com, and we do GitOps Meetup. So everything what we do here is hosted in our GitHub account. So if you want to talk, you don't necessarily need to talk to me. You just Google our GitHub account, and then you basically go there and do pull request. If it's approved, merged, then everything is set up. So we do GitOps Meetup, okay? That's how easy it is. That's it for today. And again, I'm gonna take pictures and I will post it everywhere and try to convince your manager to get like 2 weeks extra vacation because you are attending here, all right? And you, if you are manager, be ready. So tomorrow you will get some requests, okay? Cool, take care. And let's give the talk to Christian and Simon. And I just want to say one thing. These guys know what they are talking about, okay? So, stage is yours. So, great luck. No pressure, okay? No pressure. And then if you have question, you just raise your hand and you speak to microphone as I do, okay? Cool. Let's give it to you.
Hey, everyone. I'm Christian. I work as my work job is as a DNS engineer at Cloudflare. My company is on a mission to help build a better internet, and we try to do that through various ways. One of the ways I'm trying to help is by improving our DNS services, of course. I've been doing DNS for the better part of close to 20 years now. Previously at the same place as Simon has been working at, up until tomorrow. 1.com. So I was working in Copenhagen for quite a many years, doing DNS there as well, and I've been doing DNS at Cloudflare.
Yeah, so I'm currently working at 1.com for one more day. If you know anything about web hosting and so on, then tell Jacob because we want to hire people. Anyway, we do a lot of web hosting. We host about 3 million zones, I think, and Cloudflare hosts way more, but it's still a fair bit. Yeah, and I've been working with DNS for a long time too.
This talk is going to be fairly broad across DNS. It's going to involve a bit of history. It's going to be the obvious, like some of you people who already know DNS, but it's also going to be a bit into what has currently been going on about DNS that you might not know. I will be bringing up DNSSEC, but I won't be going into the details of how DNSSEC works. That would be a talk of its own, just so you know. So if you're here to sort of get the nitty-gritty on such things, sorry, that's going to be have to be a future talk.
Or ask us afterwards.
Ask us afterwards, of course. It's never DNS, as you all know. But frequently I get the question, what is DNS? My kids ask, Dad, I don't know what you're working with. Well, DNS, I'll tell them, is the phone book of the internet. That's sort of the easy explanation. But then I get the question back, what is a phone book? Kids these days, you know, I mean, they have no clue how things used to work. So we know people by names and email addresses because they're easy to remember. We don't know about digits, of course, and especially not binary. So we make things easier, and DNS is one of the early protocols. Quick survey, hands up. How many of you actually know more than 10 phone numbers by heart that contains more than 4 digits? Yeah, I thought so. I wouldn't raise my hand either. So that's sort of the easy explanation why we need DNS, because we can't really remember numbers in a good way. DNS is fairly old by now. It's turning 40 next year. The earliest specification is RFC 8082 and 8083, and these were updated in 87, and this is more the modern DNS as we know it, 1034 and 1035. 1035 is the actual implementation and contains a lot of the details. So, with that, I'm going to leave over to Simon to talk about how names are resolved.
Yes, so when you want to resolve a host name, for example, in this case, www.example.com, you would usually ask your stub resolver, which we don't have an example of here. This, in this case, it would be your computer. This one goes to a recursive resolver. This could be, for example, Cloudflare 1.1.1.1, or it could be your ISP's name server. It's the only thing it does is to do the resolving for you and cache the result. So, what would this resolver do? It will take the full host name, then the question, and it will ask the root servers. We'll go through the root servers later on. Each recursive resolver has all the root servers hard-coded, so it knows the IP number of each and every root server. It asks for the host name. The root server says, I have no clue, but I know where .com is in this case. You get a name server or NS record back. The resolver then goes to the TLD, in this case .com. It asks the TLD server for .com, and it will say, yeah, I know the name server for example.com, but I don't know anything more than that. And then you continue on, and you ask the auth server for the full host name again, and you get a result back. Yeah? I can see if I can mic it closer. Let's see here. So in this case, we have the same graph. We ask the root server. We ask, for example, .org in order to resolve Foo Café. We ask for Foo Café, and we ask for a subdomain. It's the same thing as before, but we do this in multiple steps, and we send the full host name each time. We did at least. We'll get into that later on. Let's go through this a bit. The DNS message, it's a bunch of data that's sent between the resolver and the server. The message format is the same, and we have multiple sections. We have a header, we have a question section, we have answer, and we have authority record and additional. So when you send a query, the auth server will answer back containing the exact question. So you will see that it matches. And then you have the answer, that could be the A record, and then in other cases you can have the NS records. Let's see if we can get through this. Let's go through this. Yeah, so a domain name. This can be anything. For example, example.com, SC, that is a valid domain name. And it can be whatever very long string, or just dot. Dot in this case would be the root server. Let's see if we can go through. So each label is separated by a dot. So example in this case is a label. Com is a label. Each label can be max 63 bytes long, and the whole string can be 255 bytes. So a host name can never be longer than 255, and each part can only be 63 bytes. And this is due to compression in DNS. You can get more questions. Any valid string can be represented. So you can have anything in DNS. It doesn't have to be ASCII. You can have literal dots, literal asterisks. You can have Unicode, anything is possible. It's probably not recommended, but you can do whatever you want. So you could, in theory, actually store Unicode directly in DNS. And a fully qualified domain name is one that ends with a dot. Just, yeah, so you know that it's in root.
So to make it easier to administrate things, you add a bunch of resource records into what is called a zone, and that is an administrative unit. For instance, .se is one zone, and within that zone, that can be then delegated out to child zones. For instance, foocafé.org is a delegation from the org zone. And on top of all of this, we have the root zone. And the root zone is the very start of the namespace hierarchy. This is the top of the upside-down tree. It contains delegations to all of the top-level domains. For instance, com, net, org, se, one. And that is basically all it does. But at the very heart of DNS then, what we query for are the resource records. They are the unit of information that is we really want to have from the servers. They map information to a DNS name, and depending on the various types, you have different data. You want to talk about? For instance, we have the very common address types, the A and, as we say, quad A records. They contain basic address information. In the A, it's an IPv4 address, and that's stored binary. So even if you're using a program such as dig or NSLOOKUP on Windows to do an A query, that information is converted to in a presentation format, as one frequently says. But it's in the DNS message, it's encoded as binary information. In the quad A, it's then an IPv6 address. And then there is a way to encode IPv4 addresses in a quad A record, an IPv6 address, which is a bit wonky, but it exists there. I have yet to see any valid uses for it, but yeah.
And in this case, a quad IP is just 4 times as big as the A record. So
which is where it comes from. There was an early attempt to define IPv6 addresses, and they called it actually A6, but that was discarded along the way, and quad A became the standard. Another common type is, of course, the CNAME, or the canonical name, and that is basically an alias record mapping one DNS name onto another. In my case, it's I have a CNAME, junk elmerot.se, which is the same to mail elmerot.se. And that what happens there is, instead of looking up further information on junk, it actually allows the resolver to look up the resource type on mail instead. Another very common one, which is responsible for delegation, is the NS record, and it specifies the authoritative name service for a zone. Depending on where it's defined, if it's defined on the zone apex, it is the own zone's name service, and the zone is authoritative there. If it's not on the apex, then it is performing a delegation to a child zone, and the parent zone, in this case, as we call it, the parent zone is delegating as part of the subzone. The parent is actually not authoritative for those NS records, and you can ask us afterwards why that is, because that's fairly complicated to explain, but just suffice to say that is how it is. One of the more common types, of course, is the MX record. Who hasn't specified those in a while? And that basically specifies where to route email for a zone. If you were to use an email address that actually doesn't have an MX record, there is a quirk in the protocol regarding mail, and that is that what happens then is that the mail server actually tries to look at the A record at the apex for the zone and tries to send an email there if that actually exists. Just something to know about. So if you're sort of wondering why someone is actually trying to probe port 25 on a server. As I said, a zone is a specific part of the DNS namespace, and it's managed by a specific organization. And that is a way to have all of this single DNS namespace distributed to the various interested parties around the world. A zone is defined by two records. One is the start of authority, or SOA, record, and the authoritative name service for the zone itself. And those have to exist at the zone apex, which is if I have the zone example.com, they are underneath example.com.
Technically, those NS records doesn't have to exist, but you might have problems if you don't have those.
Yeah, and the reason for that is then there exists no authoritative resource for those NS records, so that's really bad for you. Any other records are actually additional.
So within the zone itself, so this is in your own DNS server. You have, in this case, you have multiple records. We have a www, we have a wildcard, we have an app, and in this case, we have an Acro challenge. So in this case, I think we'll go through this further on, but yeah. Okay. So in this case, in DNS, you have this magic thing called wildcard. This will catch anything that doesn't exist before. For example, if you ask for www, then you will get www. If you get ask for ABC, then you will get star. DNS, in this case, is also a tree, as you can see. This means that these items here, app1 and domain key, they actually exist, but they have no data. I think we'll talk about that later on. So this is actually true within the zone too. So it's a tree on your own server too. It's not just a string. So let's go through some more record types. TXT records, they are really common. They are used for example, DKIM in mail. That's probably the most common case, and for authorizing Microsoft or whatever there is. So this standard is written in a very weird way. It's split into 255 chars strings, but you can have multiple of them. In modern name servers, for example, Power DNS, you can just say generate a string and it will split it for you. In not so modern servers, for example, Bind, it forces you to actually split it into 255 chars. So what you would do if you have a really long string is to create one with quotes and one with quotes, and then it will be concatenated to one string. And it's kind of up to the parsing end to figure out how to concatenate it. For DKIM, for example, it will concat without the space, so you just split it in this case. Yep. So we have been talking about this a bit before.
So this is a typical SOA record for, of course, my company. It designates a bunch of information. It says which is one of the authoritative name servers for the zone. So if all else fails, but I have the SOA record, I can try to talk to this one to get the zone. Next up is actually an email address. It doesn't look like a typical email address, but what happens here is you take the very first dot that exists and actually replace that with an @ sign. Okay, so I have actually have a Gmail address which has a dot in it, christian.elmerot @ something. How could I specify that one? You actually can, but then you have to escape the dots in the name part before the @ sign. So the first unescaped dot is where you put the @ sign. Next up is actually a serial number, and on some DNS providers that change, on some it doesn't. The only thing the serial number tells you is this zone, the version of this information that you're getting from the zone is under this serial number. The idea is that the serial number should change when anything in the zone changes. But if you ever try to rely on that, you're in for a nasty surprise on some providers. One of the more interesting things that happens here is a bunch of information when the zone is supposed to, when you can refresh the zone if you have cached it, things like that. But the last one is one of the more interesting one, and that tells you how long you can rely on a negative answer before you check again. So in this case, you can actually query for a name that doesn't exist, .cloudflare.com, get what is called an NX domain answer back, which means that nothing exists on that name. And then I can rely on that being true for 300 seconds before I try again. And that is what resolvers do. And that can cause some issues that we will talk about.
Yep. Stuff is actually happening in DNS. We have a few new types. I don't think these has been standardized yet. I don't think we have a finished RFC. We have HPS and SVCB. HPS is a subset of SVCB. This is a generic key value type where you can encode anything. You could, in theory, implement DNS in SVCB if you want. So, what's cool about HPS? So in HP3, we have the problem that we don't have a defined port. We might have, but we might not. And the other problem is that if you want to do IPv6 and or IPv4, then you need to ask for a record and a quad A record. But in this case, you can just ask for the HPS record. You get to know that the server supports HP3, the draft 29, and HP2. You can also see that we have hints about the IP numbers. The standard is a bit messy about if you can trust these, but anyway. Another cool feature that isn't implemented here is redirects or kind of CNAMEs, where you can specify a different server to query. So you can do CNAMEs on Apex. Okay, this is a bit weird record. We have a few of those, SSHFP, that allows you to publish a public key in DNS, and then the SSH client can trust the server to do this. And I will add that we have a more common type called TLSA. That's used so you can publish the public key of your TLS certificate in DNS. And by trusting DNSSEC, you can trust the TLSA certificate, which means that you can bypass the whole CA thing and trust the mail server directly without verifying the CA.
DNS is has specified a bunch of transports where you can send DNS messages over. And the most common one, of course, since the beginning of the days, are UDP port 53, or as we commonly call it, DO53, DNS over port 53. And that is both UDP and TCP. TCP support is actually mandatory today if you set up a DNS server. And there are various reasons why TCP support is mandatory. One of the reasons is UDP fragmentation. The original specification says a non-reliable, that is best effort method of transporting a message of 512 octets or bytes. And that's all fine. So, I mean, this is from 83. But 512 bytes is not a whole lot of data. So we're going to take a diversion and explain why we've come to a few things. And that's the tale of the 13 root servers. The root servers are the name servers that are responsible for the top, for answering for the top-level DNS zone, also known as the root zone. And if you query for the root zone by simply doing DNS, you get these answers back to you. And as we can see down here, it's a bit, looks a bit weird, but it says 229 bytes is the answer that we get back. That's actually a far bit from 512 bytes that we were talking about. But the problem is that 13 name servers and their A records is the only thing that you can fit within one 512 byte message. Hang on, we were talking about name servers. Yeah. So why do we need the A records? That's because we have kind of a chicken and egg problem here. NS records, they provide you with the name of the name server. But we talk to IP addresses, right? So how do you find the name server to talk to for the zone when the name server for the zone is located within the zone itself? And for the root zone, all name servers in the world are located within the zone itself. So we need some way to bootstrap this. And that is through glue records. Glue records are provided as A or quad A records in the additional section of the DNS message. So the glue records holds the corresponding address for the name server records. So the message actually looks like this if you query for one of the name servers itself. It gives you the name servers in the answer section, and then in the additional section you get the IPv4 addresses. And that fits just about nicely in 512 bytes. Hang on a bit. Over time, the use of DNS has changed, growing message size, but what about IPv6 for the root servers? We can't add IPv6 addresses, glue records, into this without going over the 512 byte limit. So, oh, there we go. This is actually how a modern reply looks like. And we're up to 811 bytes. Now that wouldn't work without some sort of extension mechanism. And that is comes through the eDNS, or extensions in DNS, which is from '99. And that's round about the same time as the DNS extender started to emerge. There is a correlation there. The eDNS specifies you can have opt pseudo records, which specifies additional information. And it allows you to have up to 64K DNS message size. But this is a large DNS message now. And if you're using a program such as Dig, it defaults to wanting up to 4K of DNS message. But if you know anything about networks, there is this little thing called maximum transmission unit. And that is far too often way below 4K. And that causes UDP fragmentation. And UDP fragmentation is bad. TCP fragmentation is not an issue. Everyone sort of has nice support for TCP fragmentation. But a lot of firewalls doesn't like UDP fragments. And that is all of it right now a problem, because now if you send large DNS messages over UDP, they frequently get lost. And if you don't think this is a problem, talk to me afterwards and I can tell you what happened last week at work.
And the problem is getting bigger and bigger with IPv6, where it's even worse.
Yeah. So if we then go all the way back to what we were talking about before we did this little detour and tried to explain why we all of a sudden can send more than 512 bytes. We are sending traffic over UDP, or in the case of a large DNS message, over TCP. In the clear, we have an open path attacker which can then sort of intercept the DNS message and give you a malicious answer, sending you to the wrong server, and presto, you thought you were going to the wrong site, and now all of a sudden you're going to a malicious site. So DNS, the DNS world realized they needed a solution for this, and they called that DNSSEC. DNSSEC, as it stands, that was very much a trial and error process. If you look into what is published in terms of RFCs, there is a lot of sort of records that we designed it for doing the kind of stuff that we wanted for DNS, but it didn't go all the way through. The idea with DNSSEC is that we trust what we see, but we also verify. And it's built upon public key crypto chains, where a parent zone secures a child zone. You have a DS record that exists in the parent, and that links to the DNS key in the child. And the DS record, or the delegation signer, contains a hash of the public key, of the DNS key. So this is a hash of what's in here. And with that hash, you can easily verify that that is correct. And of course, that links back to all the way up. So there is only one point of trust that you have to sort of implicitly say in all of this, and that is the root's DS record. And all of the common resolvers that we have out there, they are bootstrapped with the root's DS records. So that's the only point of trust that you have to say. And that's easy. It's very easy to verify that the resolver's DS records is the correct one. And once we have that, then we use these DNS keys to sign the record sets. And that means that a complete set, so if I have 4 A records, these 4 A records are bunched together, and the DNS key is then used to create a signature, and with the signature, a third party can take and verify that the data is correct. Like I said, and these signatures are called RSIGs. Quite frequently, if you want to check RSIGs on a zone, you can't directly query for that. If you do it against Cloudflare's DNS servers, you get a refuse back. And the reason for that is we do what is called live signing. One.com uses that as well, and that means that the signatures are generated on the fly. That means if you query for an RSIG, the server actually doesn't have any information to create the signature for. Besides, let me step back once. RSIGs are only supposed to have any valid within the current session as well. So if you do a query for a TXT record and you get an RSIG, you can only use that RSIG for the TXT record that you received in that query. So you can't take the TXT records from a query you do 10 minutes later. They might match if the TXT records hasn't changed, but you can't count on that. So an RSIG that you receive within a query response is only valid for that response and not the next one that you repeat. And the signatures, they validate the records and the contents. Do you want to talk about the next?
Okay, so DNSSEC, that is not privacy. We don't add any encryption. You can still read the content as much. It's clear, sent in the clear, but you can trust the content. You can trust that it's the valid content you get. So you can't do, for example, man-in-the-middle attacks. Yeah, again, it ensures that the content is correct, but you can still see it. So yeah, DNS has a privacy problem. Obviously, DNSSEC public, you can see everything being sent if you are able to do a man-in-the-middle attack, and this is clearly a problem because you might leak information, you might tell a state, for example, that you're into some information that they don't want, and yeah, any secrets shouldn't be in DNS servers. And I can tell you this: so there's a lot of companies that, for some reason, think that DNS is secret, so they keep the zone really secret, but basing security on that is a really bad idea. So again, DNS is chatty. It sends everything in clear text. It actually sends the whole string, the whole query, to every result or every observer it asks. And in this case, yeah, so it leaks it to every resolver and every observer on the way. So you leak the whole query to the root. So if it asks for www.foocafé.org, it will send the whole string to the root. Anyway, so we have this nice new feature called QNAME minimization, where the resolver will split the hostname into each label, and it will try to send each part to the observer and see if it gets a valid answer back. This means that it will not send the whole www.foocafé.org to the root server. It will only send org to the root server and see if it gets a valid answer back. And it will not ask for the type you ask for. It will just ask for a record because that's the most common thing.
So with Snowden revelations, there came a realization in the DNS community that something had to be done about DNS privacy as well. And what the IETF did was create a work group that still exists, and it's called DPrive. And it works on making privacy in DNS better. And the first thing that came out of that was to do DNS over TLS transport, or DOT. And that's basically sending a DNS message inside a TLS session. So you start a TLS session towards your name server, and then you send your DNS message within that. So nothing really complicated, but the traffic all of a sudden is encrypted. This happens over TCP port 853, and that's important to remember because there was a suggestion that you should be able to do this over UDP port 853, that is send datagram over TLS as well, but that never amounted to anything. That was dead in the water.
Yeah, I can add one more thing that, and by having a different port, you can do an attack where you block this port, and the client will downgrade to unencrypted, and then you lose all of it.
Yeah. One of the early supporters for this was Android. That went off to an early start. But as Simon said, it's very easy to block this. And the community, the wider DNS community, then realized we need something different to do that. And that came with DNS over HTTPS, or DOE. We should have put in a Homer Simpson picture here, of course. But what happens is that you send DNS messages inside an HTTPS 2 or 3 session. The traffic is encrypted because it's HTTPS. It happens frequently over TCP port 443, normal HTTPS traffic. Support in Chrome and Firefox, of course. And it evades some of the blocks against DOT, because who blocks that one? Right? And all of this is possible because when they evolved HTTP to HTTP2, they also made it a binary protocol. So it wasn't possible before HTTP2 came along. So, you remember the wildcards that we were talking about. How do wildcards actually work? The important thing to remember about wildcards is that any wildcard only apply to anything that isn't explicitly or implicitly defined in the DNS tree. So any branch that explicitly exists is actually not something that the wildcard can be used for. And that frequently comes out to bite people. So, for instance, in this case, we have example.com. All of these names exist. So select the one .domain key .example.com exists as a name. _domain key .example.com exists, though there is no record attached to it. And this means that this is a name that has no records on it, and we call those empty non-terminals. But if I then try to query for domain key example.com, I get an empty answer back. But I don't get an NX domain which says this name doesn't exist. Hang on. Because it actually does exist. The name exists, it just doesn't have any information attached to it. So this is what we call a no data answer. No error, no data. Why doesn't the wildcard apply to it? Because the name actually exists, right? Which makes it very easy to see that if I then query for blog.example.com, that name doesn't exist here in the tree. Now the wildcard can apply. But it can only apply for the A record type that the wildcard has defined. So if I try to query for mx.blog.example.com, this wildcard will apply to it.
And this actually shows a real example that we had in production. We had a Kubernetes cluster running. We had a wildcard pointing to the ingress. So whatever name you ask for example, app1, will be sent to Kubernetes. But while we do DNS or do certificate ordering, we create a more specific empty non-terminal, in this case app1, and we create ACME challenge, which is a TXT string used to verify the certificate. So during the time while we ordered the certificate, this empty non-terminal would have had higher priority than the wildcard, so the application stopped working during the time you did the ordering, and then it started working again.
So assuming you already have a wildcard at starexample.com, and you want to cover banana, grape, etc. with a wildcard, then you would need to create star.fruitexample.com because these other names exist. There is something missing here, I'm afraid. Sorry? Yeah. I'd like to just briefly go through some recent development that is happening on the DNS area before we stop this. There is a development that has been primarily proposed by Apple that is called Oblivious DNS over HTTPS, or ODO. And that's basically DNS privacy on steroids. What happens is that you insert a proxy in between your resolver and your authoritative server. The traffic is encrypted, so that happens over, as the traffic happens over HTTPS. The resolver here encrypts the query that it sends, and then forwards the message to the ODO proxy. The proxy then passes the query to the authoritative server, which sends an answer back. But the thing is, the authoritative server doesn't know who's querying in this case. It just sees the proxy's IP. So all resolvers out in the world will use the same proxy for the same authoritative server. So the only thing the authoritative server sees is the proxy IP. But the resolver has used the authoritative server's key to encrypt the information. So the authoritative server can decrypt the query that the resolver sent. So there is a separation between the query and the client who's asking. And that makes this very secure. And to finalize, that there is support for this in iOS right now. Oop. What happened? Just before we go to food, DNS over QUIC is another thing. How many here know about QUIC? Good, quite a few. DNS over QUIC is very interesting, and that's, of course, sending DNS inside a QUIC connection. The traffic is encrypted. It's happening over UDP port 853. Remember, DNS over TLS was TCP port 853. So the community took and reused the UDP port 853 because they could. The datagram over TLS wasn't the thing. There isn't much support for it yet. That is emerging. But early experiments show that it's faster than DNS over TLS. Frequently issues that we encounter is, I would say, down to among these three. NX domain. I can't resolve the name I just added. Frequently that's because before you added the record, you queried for the name. So now the negative answer is actually cached. So you have to wait for the negative cache time to happen before you can actually see the record. Another thing that happens is the wildcard isn't working, or it's not working as you hoped it would. And that's usually because some name is defined in your tree implicit by another record. And finally, why can't I have CNAMEs at the zone apex? That dates back all the way to the early RFCs that says CNAMEs can't exist alongside any other records. And then they made a modification for DNSSEC except RS6 and NSEC3 records. That is why you can't have it at the apex, because you already have the SOA and you have the NS records and anything else. That is sad but true. Yeah. And that is about that. So thank you very much for listening, and we'll of course be around and answer any and all questions that you have, hopefully.
Thank you very much. So what we are going to do, Pizza doesn't like to wait, and Pizza is already there. Okay, so we just give you two questions option, like two questions you can ask. And for online people, if you are going to write something on YouTube, we know that 1 million people is looking, so just feel free to type. We will answer them on live streaming, but here we have only two questions that we can ask. Anyone want to ask a question? Yes?
My question is about the HTTPS record. I didn't really get a grasp of what it does. So there was an IP hint, and that's what I understand is that it falls back to that IP in the IP hint, right?
That is correct. The hints exist as a replacement for doing a second query for the A or quad A records.
Okay, in that case, the cloud, the DNS provider query does the query, right?
Yeah, or you define it beforehand.
Okay, so in that case, is there a built-in for restricting what you can query in the IP hint? For instance, let's say I have a malicious, I want to query something internal to the cloud, to the cloud provider. Sorry, to the DNS provider. Okay,
so what you put in the, you decide, the zone owner decides what you put into the HTTPS record.
Okay.
The problem with this record is that it's kind of undefined what to do if you have information about the existing A records or quad A records. So it's just a hint. You might not trust it. Okay. The RFC is very fluffy about that.
But suffice to say, for instance, Safari is very early on has been very early on supporting this. The driving engineers behind this is a bunch of Apple engineers, and so very early on we could, as Safari gained support for this, we could see that HTTPS queries were coming in, but they didn't get any answer back, and then they were falling back to doing A and Quad A queries.
Another important thing that Quad A contains, I don't know if we had that in the example, and that is the public key for something called encrypted SNI, or encrypted client hello. So when you do a TLS connection today, normally, you send the host name to the server in clear text. So you actually leak that, even though you do encryption, because you need to tell the server which cert it should serve. So there's this new thing called encrypted client hello, and in order to be able to trust the public key, you publish the public key in DNS, in this magic record.
In the HTTPS record, yes.
We have one last question. Go ahead.
Does Odo require support for from every authoritative server?
Yes, unfortunately it does.
Okay, then I have one other question about CNAME. Maybe you could tell us why my CNAME is not resolving HTTPS. Why people don't get that its CNAME is not an HTTP proxy server?
Well, I think the question is, why doesn't your web server answer to whatever name you pointed it to? And the reason for that is in HTTP, you actually send the host name part of the HTTP request you do. So you send it as a host header or auth header in HTTP 2. And it's the same with TLS. For example, if you try to connect to Cloudflare without sending a server name, or wildcard for that, say you will just get an error back. You will not get a certificate back. You will get an error message back. So if you just point whatever name to some server, the server need to know about this host name. And if they don't, they will just tell you 404 doesn't exist. So in the case of one.com, if you just point a domain name to some existing account, you will get a 404 because we don't know how to handle it. We don't know how to point it.
Yeah, and CNAME is not HTTP proxy server, so you just can't forward HTTPS traffic. So just people who fall into this. I mean, I have been there. Probably all of you have been there. So do not expect HTTPS traffic to be forwarded as CNAME. So cool. Then pizza is there, and if there is any more question, speakers are here, so go and personally talk to them. And we would like to thank Foo Café for hosting us today. And we have one great company, Capiche. Is someone from Capiche here? No, so they usually host our meetups. They sponsor our meetups. So big thanks to Capiche for sponsoring Foo Café and our meetups. And thanks Foo Café again for hosting us. Yep, thank you.